For centuries, people have looked to the stars and wondered about the universe. What is out there? How did it all begin? Why we are here? In the 20th century, scientists finally developed a theory called the Big Bang, the cosmology of which seeks to answer these questions. It's the idea that our universe began in a Big Bang. It explains the expansion of the universe, the large-scale distribution of galaxies, the cosmic microwave background, and much more. However, some observations don't fit the standard model. Things just got worse, as in 2023, NASA's new James Webb Space Telescope cast even more doubt on the standard model as it detected the object that no one expected in space: the existence of stars with an estimated age that is older than the universe itself. But how is it possible? How can a star be older than the universe? Does the death knell of modern cosmology ring? And do we need a new model of the universe? A new cosmology? All this and more will be revealed in today's episode of Eyes 200. About 200 light-years away, near the constellation Libra, an ancient star with a very boring name, at 140,283 careens through our galaxy. Its breakneck speed hints of its dramatic history 12 billion years ago, when the progenitor of the Milky Way gobbled up the dwarf galaxy that was its home at the time. But the most interesting thing about HD 140,283 isn't its speed, it's its age. It is one of the oldest things we've ever observed. Given its extreme age, HD 140,283 has been unofficially dubbed the Methuselah star, named for Methuselah, a biblical patriarch who is said to have died aged 969, making him the longest-lived of all the figures in the Bible. Early estimates of its age were in the ballpark of about 16 billion years. The most modern estimate of its age is 14.46, with an uncertainty of 0.8 billion years. Such a figure was rather baffling. After all, the age of the universe, determined from observations of the cosmic microwave background, is 13.8 billion years old. So how can a star be more than billions of years older than the universe? Surely that is just not possible. Either the star was older than the universe, or the universe was not as young as scientists thought it to be. Or maybe the dating was simply all wrong. If so, what was it to be? Let's find out. First, you should know age is hard to measure for objects in space. Stars like the Sun maintain the same brightness, temperature, and size for billions of years. Planet properties like temperature are often set by the star. They orbit rather than their own age and evolution. Thus, determining the age of a star or planet can be as hard as guessing the age of a person who looks exactly the same from childhood to retirement. Fortunately, stars change subtly in brightness and color over time. With very accurate measurements, astronomers can compare these measurements of a star to mathematical models that predict what happens to stars as they get older and estimate an age from there. Stars don't just glow, they also spin. Over time, their spinning slows down, similar to how a spinning wheel slows down when it encounters friction. By comparing the spin speeds of stars of different ages, astronomers have been able to create mathematical relationships for the ages of stars, a method known as gyrochronology. A star's spin also generates a strong magnetic field and produces magnetic activity, such as stellar flares, powerful bursts of energy and light that occur on stars' surfaces. A steady decline in magnetic activity from a star can also help estimate its age. A more advanced method for determining the ages of stars is called asteroseismology, or star shaking. Astronomers study vibrations on the surfaces of stars caused by waves that travel through their interiors. Young stars have different vibrational patterns than old stars. By using this method, astronomers have estimated the Sun to be 4.58 billion years old. Now, let's shift the attention back to the Methuselah star. How are astronomers able to ascribe such an ancient age to the star? There are several distinct different populations of stars in the universe, delineated by the amount of metals in them. Our own Sun is a population 1 star, with a significant amount of heavy elements. The Methuselah star is a population 2 star, with considerably less heavy elements, especially iron. There is another hypothesized class of stars called population 3, which contain essentially only hydrogen and helium. No population 3 stars have been observed. The 3 distinct classes of stars began their lives in different eras of the universe. Shortly after the Big Bang, the universe consisted of essentially only hydrogen and helium. Counting atoms, the ratio was about 92 hydrogen and 8 helium. Since each helium atom weighs about 4 times as much as a hydrogen atom, the ratio is about 75 hydrogen to 25 helium when expressed in terms of weight. Population 3 stars formed very early on in the universe, composed solely of the primordial brew. They were huge and hot, and they burned through their fuel in a cosmological blink of an eye, converting hydrogen and helium into heavier elements. These stellar monsters exploded, mixing some of these heavier elements into the cosmos. Population 2 stars formed a little later, but still very early in the history of the universe. Their original ingredients were still sparse in heavy elements, especially iron. Many of these population 2 stars lived their lives through the stellar life cycle and themselves exploding as supernovae that further salted the cosmos with an even richer mix of heavier elements. Population 1 stars, of which our Sun is an example, condensed out of gas clouds enriched from the death throes of early population 2 stars. The different mix of elements has consequences on the details of the fusion processes in their core. Since the Methuselah star is a population 2 star, it is old. In 2013, the Hubble Space Telescope used its fine guidance sensors to precisely measure its distance, which allowed astronomers to determine the star's intrinsic luminosity. By combining the luminosity and spectral information with advanced models of star formation and evolution, the researchers estimated an age on the Methuselah star of 14.46, with an uncertainty of 0.8 billion years, older than the accepted 13.8 billion years, older than the accepted 13.8 billion year lifetime of the universe. So, is this a huge problem for the theory of the Big Bang? Well, it's still a puzzle. That's because the central value of the estimate for the age of the star is only part of the story. The uncertainty must be taken into account. And when the uncertainties are understood properly, it means that the actual age of the Methuselah star has a 70% chance of being between 13.66 and 15.36 billion years old. First, the lower estimate is within the accepted age of the universe. But second, there is a 30% chance that the Methuselah star's age is outside that range, with a 15% chance that it is even lower. When you take everything into account, given the Hubble measurement of the age of the Methuselah star, it is at least 20, likely its actual age is lower than the 13.8 billion-year-old age of the universe. 20% is roughly the same as the chances of rolling a 6-sided dice and it coming up 6. It's pretty likely, and that is assuming that there are no unaccounted for uncertainties in the age estimate. However, there is no doubt that the Methuselah star is old. Indeed, it is the oldest star in the universe, for which there is a fairly precise estimate of its age. So, instead of wondering whether Methuselah really be more than 2 billion years older than its environment, let's look at the problem in a different way. Is it possible that the universe was not as young as scientists thought it to be? Well, frankly, it's hard to even fathom the immensity of 13.8 billion years. If the entire history of the universe were stretched out into a cosmic calendar, with the Big Bang being the greatest New Year's fireworks display to ever exist, then the Earth doesn't even join the party until mid-September. Oh, and the entirety of recorded human history only happens in the last 10 seconds on December 31. Scientists calculate the age of the universe by observing light emanating from stars born only a couple 100 million years after the Big Bang. Because the universe is also expanding, It stretches that primeval light, which scientists call redshift. Calculating both observable distance and universal expansion implies a universal age of 13.8 billion years. But what if the universe was actually even older than scientists believed? Well, it turns out that it might be much older. A new study by scientists at the University of Ottawa suggests that the universe is actually twice as old as we previously thought, at around 26.7 billion years old. Rajendra Gupta, adjunct professor of physics at the University of Ottawa, bring into the calculus a 1929 theory from Swiss astronomer Fritz Zwicky. The theory claims that photons get tired as they travel across vast distances and lose energy over the course of billions of years. While this conflicts with observable redshift data, Gupta says that by allowing this theory to coexist with the expanding universe, it becomes possible to reinterpret the redshift as a hybrid phenomenon, rather than purely due to expansion, in a press release. His results were published earlier this month in the journal Monthly Notices of the Royal Astronomical Society. Increasing the universe's age could help explain some long-standing cosmological quandaries, as well as some new ones discovered by NASA's James Webb Space Telescope. To arrive at 26.7 billion years, Gupta combines the tired light theory with the idea of evolving coupling constants. This concept was originally proposed by theoretical physicist Paul Dirac, and suggests that interactions between particles might have varied over time. This wouldn't be the first time that scientists have revised the universe's age. In the 1920s, Edwin Hubble thought the universe was only 2 billion years old. But our calculations have only gotten better over time, and doubling the universe's age is quite the leap. So, only time will tell if astronomers revise the universe's age based on Gupta's work. But whether humanity's recorded story represents only 10 seconds or 5 seconds, the fact remains, the universe is an old and amazing place. Put the age of the universe aside, there's something strange going on with the Milky Way. Recent measurements suggest that stars at the outskirts of our galaxy are misbehaving. They're traveling far slower than similarly situated stars in other galaxies. One possible explanation for the Milky Way's stellar slowpokes is that our galaxy is extraordinarily deficient in dark matter, the invisible substance thought to serve as gravitational scaffolding for cosmic structures. Another is that our core conceptions about dark matter, such as how much of it exists in the universe, are somehow deeply flawed. This head-scratcher stems from the European Space Agency's Gaia satellite, which provides unparalleled information on the speeds and positions of nearly 2 billion stars in the Milky Way. Last year, the Gaia team released the space-based telescope's most precise measurements yet, spurring astronomers to refresh their galaxy, spanning assessments of stellar behavior. Several independent groups have now reported the oddly sluggish orbits of stars along the Milky Way's outer rim, the peripheral edge of our galaxy's luminous whirl. Stellar speeds offer a way to weigh a galaxy. The gravitational force each particular star feels depends on the galaxy's total mass. A Gaia-derived study released on September 27 in the journal Astronomy Astrophysics pegged the combined mass of our galaxy's gas, dust, stars, and dark matter at some 200 billion times that of our Sun. Hefty for you and me, but on the order of 5 times less than that found in several other earlier assessments. Because the Milky Way's visible material hasn't disappeared, one easy and especially thought-provoking way to explain this result is that far less dark matter is floating around than previously believed. Then again, weighing a galaxy is a notoriously tricky business, so it's possible that errors lurk in Gaia's data, or the new analyses that create the illusion of the Milky Way as anomalously trim. But the fact that multiple teams have seen the same result gives more substance to the findings. If true, they could force a rethink of fundamental physics and prompt a re-examination of all other galaxies in the universe. Let me put it this way, says Stacy McGaugh, an astronomer at Case Western Reserve University, who wasn't involved in any of the recent studies. If it worked out that way, it would be revolutionary. In the 1970s, astronomer Vera Rubin and her colleagues began measuring stellar motions in other galaxies. Stars around a galaxy's periphery were expected to orbit at a more leisurely pace than those closer in, much like how Neptune meanders around our Sun every 165 years while Mercury zips about in 88 days. Yet, strangely, Rubin and her associates found that outlying stars were traveling at roughly the same rate as their more central siblings, suggesting that an enormous reservoir of hidden material in and around each galaxy was gravitationally tugging on the far, out stars to boost their speeds. This invisible stuff, already then called dark matter, was surmised to form immense halos surrounding galaxies, outweighing the visible material by a factor of 10 for large galaxies and as much as 100-fold for dwarf galaxies. Measuring how everything in our galaxy moves while stuck inside of it is not the easiest task. So astronomers have tended to assume that stars in the Milky Way behave much like those seen in other galaxies. The Sun, located roughly 26,000 light-years from the galactic center, orbits around it at about 500,000 miles per hour, or 800,000 kilometers per hour, and most observations of other stars within and beyond the Milky Way have supported the idea that stellar speeds farther out should be broadly consistent with that of our home star. The Gaia satellite, which was launched in 2013, offers the best yet test of this simple notion via the spacecraft's extraordinarily precise measurements of the three-dimensional positions and motions of stars in the Milky Way. But this testing has been a gradual process because the precision of Gaia's reckoning improves in lockstep with how long it observes its stellar sample. Using Gaia, theoretical physicist Francesco Silos Labini of the Enrico Fermi Study and Research Center in Italy and his associates saw subtle hints of a decline in the Milky Way's stellar speeds a few years ago. Those hints became much more obvious in Gaia's most recent data release from 2022, which pegs stellar motions with twice the precision of a previous offering from 2018. Such improvements allow astronomers to plot the paths of stars with greater accuracy and out to much farther distances than before. This year alone, 4 different papers have revealed a precipitous decline in the speeds of stars out to 100,000 light-years from the Milky Way's center. The recent astronomy astrophysics study refers to this fall-off as Keplerian, meaning it is like that seen in the planets in our solar system, whose motions were first accurately described by 17th-century German astronomer Johannes Kepler. Such a finding flies in the face of all expectations. Minus a few minor deviations, plots of stellar orbits in other galaxies consistently show stars from center to rim, all whirling with similar speed, as if held in dark matter's gravitational grip. But for the moment, and this is what is very interesting, we do not find any other galaxies showing this Keplerian decline, says Francois Hammer of the Paris Observatory, a co-author of the recent astronomy astrophysics study. In a broad sense, the idea that the Milky Way is unique among all galaxies contradicts a basic tenet of cosmology, which holds that there's nothing special about any particular place in the universe. The findings create more specific headaches because of the extrapolated lower mass estimate of 200 billion suns for our galaxy. Astronomers are quite confident in their measurements for the visible material in the Milky Way, which amount to a mass of circa 60 billion suns. If both figures are correct, this implies that the dark to ordinary matter ratio is just 2.3 to 1, far less than the 10:1 ratio found in galaxies of similar size. Given that the perception of a downsized Milky Way emerges from several independent analyses, some researchers believe that while the decline may be genuine, it's not representative of our galaxy as a whole. Stars even farther out and currently beyond the limits of Gaia's high-precision scrutiny may well display a corresponding rise in speeds to offset the anomalous dip. I'd be very surprised if it just keeps going, because then there'll be a lot of things that break all at once, says astrophysicist Lena Nassib of the Massachusetts Institute of Technology, a co-author of one of the other papers on the decline in stellar speeds, which was posted on the preprint server archive.org. Her idea is backed by multiple lines of evidence. The Large Magellanic Cloud, which sits around 160,000 light-years from the galactic center, is a satellite galaxy that orbits our own at more than 650,000 miles per hour, or 1 million kilometers per hour, a value consistent with standard dark matter models. Another line of evidence comes from stellar streams, remnants of small galaxies and star clusters that got too close to the Milky Way and were shredded by its gravity. These stellar streams arc out to great distances and provide estimates of our galaxy's mass that line up with the weightier approximations. There's also the possibility that these different teams are inadvertently misinterpreting their data in some way. At the University of Pennsylvania, astronomer Robin Sanderson makes simulated Milky Ways on a computer, and then imagines what sorts of maps a virtual Gaia satellite would see if placed inside them. Any such plot requires certain assumptions that affect its results, she says, such as the overall shape of the galaxy's distribution of dark matter. My group has looked at how those overly simplistic assumptions, which everybody knows are overly simplistic, lead to a strange result where the model still describes the data but doesn't necessarily correspond with the realities of the underlying system. She says, Sanderson, who wasn't involved in any of the papers, is skeptical of drawing firm conclusions from them. She points out that while Gaia provides unrivaled 3D information, the uncertainties on its stellar speed measurements grow the farther out in the galaxy it looks. Future data from facilities such as the Vera C, Rubin Observatory, originally called the Large Synoptic Survey Telescope and renamed in 2019, will hopefully be able to find stars in the outer parts of the Milky Way that can help settle the debate. Gaia's next release, expected at the end of 2025, could also provide more accurate information. Hammer is eager to more closely examine other galaxies and see if their stellar speeds might also show declines, similar to the Milky Way's. For McGaw, the episode represents part of a normal, healthy churn expected from any mature research community. It's going to take a while to settle out, but I think we'll learn things in the process, he says. Nassib agrees and says she finds the current debate more exciting than troubling. Yeah, it's weird, she says, which honestly makes for cool science. I love when things are weird. Well, to be honest, what they said was very convincing. From the backyard of our own solar system to the distant shores of the cosmic ocean, the universe is full of mysteries. It has always been like that. Centuries ago, ancient astronomers were mystified by the nature of comets and wondered about the chemical makeup of stars. These old riddles are now solved, but as bigger telescopes and more sensitive instruments peer deeper into space, they have been replaced by new conundrums. To date, everything we know, everything we see, is just 5 of everything in the universe. The remaining 95 of the universe is stuff that we can't see, don't yet understand. An extraordinarily vast portion of the cosmos is still unknown. Despite the technological advancements of the last century, even with computers at our fingertips and the worldwide internet and space-based observatories mapping the far reaches of our universe, there is still so much that we don't understand. We have grown leaps and bounds since the days of the ancient Greeks and Egyptians, even since Copernicus and Kepler. But in many ways, we are still novices playing with toy models, seeking to understand the stars. At the end of the day, we are on a lone planet dangling in space, orbiting our sun amidst millions of other stars in a small corner of a galaxy in an ever-expanding universe. It is in our nature as humans to seek meaning in the stars, but sometimes the answers aren't the ones we were searching for. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.